Okay, so we're going to go through sections 2.4 and 2.5. So starting off with section 2.4, this is derivatives of trig functions. And we're not going to prove anything in this. We're just going to state what the formulas are and then go through one or two examples. But I do want to give you just an idea. Okay, so suppose we were trying to determine what the derivative of the sine function is. Okay, so this is what the sine function's graph looks like. Something like this. We know it's periodic, it waves, it takes 2 pi to get through one complete cycle. So this is minus pi right here, this is pi over 2. This is 3 pi over 2, like this. Okay, and so the way that we might try to figure this out, let's see if I'll use a different color here. What we've been talking about in class is that any place where the function has a horizontal tangent line, the derivative is equal to 0. So that means that if this is the sine graph, so this is sine, then the derivative of sine should pass through the x-axis at this point and at this point and at this point right here. Okay, so now what about these other locations? Well, here the slope is positive. In fact, if you zoom in on the graph, you'll see the slope is about 1. And so the derivative of sine has to pass through height 1 right here. And then similarly down here at pi, it's a slope of minus 1. And so we should be at minus 1 at this location right here. Okay, so if you try to draw a graph that passes through this point, this point, this point, that point, it should look something like this. Okay, something like that. Now, if you're really following along closely, and can you be, okay, that's showing up, I was just checking for a minute to see that color was showing up on the camera. This looks like the graph of cosine, and in fact it is the graph of cosine. Okay, so that's our first rule. The derivative of sine, the sine function, is equal to cosine. Okay. Now you can do exactly the same kind of analysis except flipping these two, so using the graph of cosine and asking where its horizontal tangents are, and you'll see that you might convince yourself that the graph of the derivative of cosine is equal to the function minus sine. Okay, so these are our two principal results here. Okay, let's take a look at some examples of these. All right, so suppose we wanted to compute the derivative of the function, let's say x squared times sine of x. Okay, so this is a product of two functions. It's one function here, f of x is x squared, and then another function here, g, is the sine function. Okay, so if we apply the product rule, then we know how to do this. The answer, the derivative of this function, is, according to the product rule, the derivative of the first function, okay, times the second function left all alone, plus the first function left all alone times the derivative of the second function. Okay, so here we know what these are. This is 2x, so 2x times sine of x plus x squared, and then the derivative of sine is cosine. So this is an example using the product rule. We can now compute another example, the derivative of the tangent function. So tangent of x, its derivative, well, we compute it by using the definition of the tangent function. The tangent function is defined as sine over cosine, and so now we can use the quotient rule here. So apply the quotient rule. Okay, we've got one function in the numerator, one in the denominator. So our quotient rule says that you take the derivative of the top function times the bottom function left alone, minus, leave the top function alone, times the derivative of the bottom function, like this. And we divide through by the denominator function squared. Okay. So if we simplify this, okay, the derivative of sine is cosine, so we get 2 copies of cosine here. We write that as cos squared, like this. That is the notation for cosine times cosine. So that is just a little bit of notation, maybe just a side note. This is how we write things. If we want to square the sine function, we typically write this with the 2 up at the sign like that. That's just notation. Okay, and so here we have minus sine, and the derivative of cosine is minus sine, so we get 2 copies of minus sine here. So we actually get sine squared there, because there's 1 copy there, and then 1 copy we will get from the derivative of cosine, over cosine squared. And if you remember your trigonometric identities, cosine squared plus sine squared of the same input is always equal to 1. And so this is 1 over cosine squared. Another way that we write this cosine is 1 over cosine is the secant function, and so this is secant squared of x. Either of these is fine, they're both the answer. But that's the derivative of tangent, so the derivative of tangent is secant squared. We'll do problems in class about the other trig functions. All right, that is pretty much all of section 2.4. Let's do one more question from here. So what is the 22nd derivative of sine of x? Okay. All right, well, so we want to take 22 derivatives of this, but that seems a little laborious. Okay, so if our function f is sine, then we know what its derivative is. F prime is cosine. And we know what the derivative of cosine is. It's minus sine, like this. And then we know we can take the third derivative of this. So this will be minus times the derivative of sine, so that will be minus cosine of x. And then the fourth derivative will be minus times the derivative of cosine, so that's minus cosine of x, which is cosine, or sorry, the derivative of this, minus sine, pardon me, which is sine of x. Okay, so that tells us here, look at what happened. The no derivatives is sine. After you take 1, 2, 3, 4 derivatives, you come back to where you started. So this tells us an easy way to compute the 22nd derivative of sine of x, because we'll know that since it repeats every 4 derivatives, all we have to do is look 2 derivatives past that. So if we extrapolate this, then we'll see that the 20th derivative of this will be sine of x, and that means that the 21st derivative and the 22nd derivative we can just read off of the first and the second derivative. So we get cosine of x and minus sine of x. So this is the answer here. Now notice all we did was use the fact that the derivatives of the sine function cycle every 4 derivatives. Okay, so and when you get to this copy of 4, you'll be back at sine of x, and then you just have to take 2 more derivatives. So you should be able to answer. So as an exercise, maybe answer what is the, I'm just going to make one up here. What is the 39th derivative of cosine? Okay, try to do that on your own. Okay, very good. So that's section 2.4. Section 2.5 is the section on the chain rule. Okay. So the chain rule, some of you may have had some exposure to the chain rule in your calculus classes in high school. The chain rule is about taking derivatives of compositions of functions. So this is about, the idea here is about taking derivatives of function compositions. compositions. Okay, so let's take a look at an example of this. Something simple. X squared plus 1 cubed. Okay, just as an example. How could we begin to compute the derivative of this? We have some rules we could apply. We could try multiplying this x squared plus 1 times itself 3 times, expand that out, and just take the derivative like it's a normal polynomial. But what if I wrote, so we could do this using the could do this by expanding. And just using the rules we know. Okay, but what about something like x squared plus 1 to the 19th power? So how would you take the derivative of something like this? Okay. I don't want you or anyone, certainly not me, but definitely not you, to multiply x squared plus 1 times itself 19 times to get some big polynomial and then just use the power rules that you know. That would be ridiculous. So we need another way to do this. And the key idea is to recognize that x squared plus 1 to the 19th power is a composition of two functions. So it's one function inside of another. So what are the two functions? Well, the inside function, g, this is the inside, is x squared plus 1. And the outside function is the function where you takes x and raise it to the 19th power. So x to the 19th. So if this is f and this is g and you compose them with each other, then you get this function right here. Okay, going backwards a little bit, f of g of x is g of x raised to the 19th power, which is x squared plus 1 to the 19th power. Okay, so that's the key idea here. In order to compute a derivative of a function like this, we need to be able to recognize that this function is two functions composed with each other. Okay, so here's the rule for this. So the chain rule says that if you want to take the derivative of two functions composed with each other, then what you get is you take the derivative of the outside function with the inside function left inside of the derivative as it is, and then you multiply by the derivative of the outside function. Okay, so let's see this in the previous example. So if we want to take the derivative of x squared plus 1 to the 19th power, okay, so we're taking the derivative of this function, then we had an inside function here, g, which was x squared plus 1, and we had an outside function, f, which was x to the 19th power. Okay, f prime is easy to compute in this case. You take the 19 down and drop the power by 1, and g prime is also easy to compute in this case. It's 2x. Okay, so now let's use this data and the formula for the chain rule to compute this derivative. So we take the derivative of f and plug g in. Okay, so the derivative of f is 19 times the input to the 18th power. So here's the input. Okay, so this is the derivative function of f with g plugged into it instead of x. Okay, and then we're multiplying by 2x, which is the derivative of g. Okay, so this is in fact the derivative of this function. Notice how easy that was to compute. Okay, let's do another example. So suppose I wanted to compute, let's call function h, let's say sine of the quantity 4x cubed plus 2x. Okay, so here we have an inside function. It's whatever's inside of the sine function in this case, so that's 4x cubed plus 2x. And then we have an outside function, which is the sine function. Okay, so notice if you take f and put g inside of it, then you get h. This is the key idea again, recognizing that this function is a composition of two functions. Okay, so there are two functions. We can compute their derivatives pretty easily. The derivative of sine we just learned is cosine. The derivative of 4x cubed plus 2x is 12x squared plus 2. We all know that. And so our answer to the question, what is this? We can compute that using the chain rule. It's the derivative of f with the function g inside, left alone, times the derivative of g. So, okay, the derivative of f is cosine of x, so we take cosine and we plug g into it. So g is this function, 4x cubed plus 2x. And then we multiply by the derivative of g. Being careful about parentheses here, we're multiplying by the whole function g prime. So not just that, but the whole thing. And this is the answer, okay, for that. You might see another notation in the book. And that is that if the function y is equal to f of u and u is equal to g of x, then this is the same thing as, so u is g of x, so y is f of g of x. Then we might write something like this. dy dx is the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. So here's the derivative of y with respect to u, that's the derivative of that function, times the derivative of this function with respect to x. We'll see this notation from time to time. Notice it's very suggestive because you want to cancel those du's, and kind of that's what's going on. But I mention this only as something that you may see from time to time in the textbook. Okay. Let's do another example. So if we have the function the square root of x squared plus 1, this is also a composition of functions. The inside function g is what's inside the square root, and the outside function little f is the square root of x. Okay, so that makes f equal to, big F equal to f of g of x. And so we can compute the derivative of big F as the derivative of little f with g left inside of it times the derivative of g. Okay, let's just on the side compute these derivatives. The derivative of little f is the square root of x, so we bring the power down and drop the power by 1, so we get something like this. Another way to think of it is it's a half times x to the minus 1/2. That was the application of the power rule here. This is because square root of x is x to the 1/2. Okay, but this is the part that we're focusing on. And then g prime is the derivative of x squared plus 1, so that is just 2x. So we can finish this off. Derivative of f with g plugged into it, that is 1/2 the square root of x squared plus 1. And we are multiplying this whole thing by the derivative of g, which is 2x. So 2x. So if you'd like, you could write this as 2x over 2 times the square root of x squared plus 1 but we, of course, would never leave it like that. We would write it like this. Okay, so there's an example of that. So let's try another one. Y is equal to x cubed plus 4 raised to the 102 power. Okay, then what is dy dx? Okay, here we've got an inside function, x cubed plus 4, and we've got an outside function, which is x raised to the 102 power. Okay, so that means g prime is equal to 3x squared, and f prime is equal to 102 times x raised to the 101. So we can write dy dx as the derivative of f, so that is 102 times the input, which is g in this case, to the 101 power, so x cubed plus 4 raised to the 101 power, times the derivative of g, which is 3x squared. Okay. You can leave your answer like this, unless you need to simplify. You can leave your answer like that. All right, let's do one that's a little bit more complicated. How about, let's take g of t to be t minus 2 over 2t plus 1, and all of this raised to the 9th power. Okay, so here I've used the letter g, so you're just going to have to get used to the fact that sometimes the inside function and the outside function have separate names. So the inside function is t minus 2 over 2t plus 1. The outside is t to the 9th power. And so if we take the inside function and put it in for t here, then we'll have our function g. So g prime of t is equal to the derivative of the outside with the inside plugged in. And then, so let's write that. So we have the derivative of the outside with the inside plugged in times the derivative of the inside function. Okay. So let's compute these derivatives really quickly. The derivative here is 9t to the 8, and the derivative here is, we have to use the quotient rule. So I'll leave this to you to verify that it's 2t plus 1 minus t minus 2 times 2 over, that's times 2, not raised to the 2, over 2t plus 1 squared. Okay, this was using the quotient rule. We took the derivative of this, which is just 1, times 2t plus 1, so we get that, minus, left that one alone, t minus 2, times the derivative of this, which is 2, all of that divided by this. Okay, so our derivative, g prime of t, is equal to the derivative of the outside function, okay, with the inside plugged in. So there's the inside function, so we get that, times the derivative of the inside. So we have to be very careful about parentheses here, but it shouldn't be too bad. I'm going to move that 2 to the front of those parentheses just for appearances, like this. And this is our answer, okay? So you'll notice, I mean, so what did we really do in this case? We just, we hopefully we'll get better and better at recognizing the inside and outside function. So we saw this is the inside function, so we just took the derivative of the outside function. So we brought the 9 down right there, dropped that power by 1, so we have 8, left the inside of this alone, and then multiplied by the derivative of the inside. Okay, that's all that we did in this case. I want to try to get this in the shortest amount of time possible. So let's just do one more very quickly. Example. So sine of x cubed plus x. Let's take, so this is our function. So its derivative is, we want to take the derivative of the outside function. We know that that's cosine. Leave the inside alone. And then we want to multiply by the derivative of the inside function, so that is 3x squared plus 1. This, okay? Should try to get better and better at this. Now let's do one more example. I want to take, let's take sine cubed of x, okay? So this is, we have an outside, so remember what sine cubed of x means. Sine cubed of x means sine of x multiplied by itself 3 times. So here we have an inside function, which is sine of x, and we have an outside function, which is x cubed. So if we take the derivative of this, then we get, well, take the derivative of the outside function, so that is bring the 3 down and drop the power by 1, but then we leave the inside function alone, and then we multiply by the derivative of the inside function. So if you wanted to simplify this, I would prefer it if you wrote that squared in the standard notation for writing powers of trig functions. So that is the chain rule. We'll go through many problems in class related to this, but they all boil down to recognizing inside and outside functions.